Gravitational wave detectors are the most sensitive instruments ever created. They are our ears into the past, capable of hearing tiny ripples in space-time that have travelled at light speed for billions of years to reach us. Gravitational waves occur because space is elastic and stretchy, as predicted by Einstein over 100 years ago. When black holes and neutron stars spiral together or stars undergo supernova, they create ripples of stretching and shrinking space that spread out and can be detected far across the universe. Gravitational wave detectors measure the infinitesimal stretching and squeezing of space-time as changes in the distance between massive mirrors 4 kilometers apart. The tiny scale of this motion pushes the detectors into the realm of quantum physics, revealing how everything we see and measure is governed by quantum physics. To understand the components of a gravitational wave detector, I have a toy model that can be easily made up. We'll use it for a few activities later in the video. It has a laser, a beam splitter, 2 perpendicular arms with heavy mirrors at each end, and where the beams recombine, a photo detector. I also have a model detector, which is a working interferometer powered by this laser pointer here. And now here is the real LIGO detector with 4-kilometer arms. The laser directs light through the beam splitter, where half travels down one arm and half down the other. At the ends, the light is reflected off of mirrors and passes back through the beam splitter to arrive at the detector. To explore the quantum physics of gravitational wave detectors, we must first examine the way we think about light. Einstein proved that light comes in quanta, called photons, little packets of energy that display 2 properties, waviness and bulletiness. In some descriptions, it's easy to think that light is sometimes a wave and sometimes a particle, but it is important to realize that light is always both. Sometimes one just dominates over the other. Because light comes in packets, measuring light is a counting problem, just like counting votes or passengers on a train. When we count photons arriving, it is their bulletiness that gives us the count. But when we add up beams of light at one place, we find that the probability of photons arriving is determined by the waviness of the photons. The probability of a photon being there adds and subtracts as if they were waves. This wave property is called interference. We can see interference when ocean waves pass an island or ripples cross in a pond. If a peak coincides with a peak, they combine to create a larger wave. If a peak coincides with a trough, they cancel out. For photons, the same thing happens. If light could take 2 alternative paths, then we get patterns of dark and light called interference. In the gravitational wave detector, the length difference between the 2 paths determines if the probability of photon detection is high, like the ocean peaks combining, or low, like the ocean waves cancelling. Now I want to tell you something amazing. If you send photons one at a time, interference still happens, as shown in this video. What is actually interfering is unclear. We like to call them probability waves. It's quantum weirdness at its best, and one of the wonderful mysteries of the universe. See how a pattern of interference builds up from single photon detections. Einstein first has a video that explains how to observe similar interference when a strand of hair acts as an island for an incoming laser beam. The rest of this video takes you through a sequence of hands-on activities where you will learn first how to use a beam splitter to make light take 2 alternative paths. The beam splitter is a key component in the interferometer. It demonstrates how photons and the entire quantum world is governed by statistics. A beam splitter does just what it says. It splits a beam of light. When photons from a laser reach a perfect beam splitter, 50% are transmitted and 50% are reflected. A CD case is a great makeshift beam splitter. We won't get 50-50, but we can shine a laser on it and adjust the angle to get 2 dots of light, one transmitted and one reflected. A little thought experiment tells us something fundamental about quantum physics. Let's ask how the beam splitter works. In the 19th century, people thought light was a wave and assumed half the wave went one way and half the other way. But knowing that light comes as photons and photon energy and photon color depend purely on their frequency, a half photon will have half the energy and be a totally different color. Partial reflections on windows are an example of beam splitters. You can see through a window, but you can also see reflections. Do you notice a colour change when looking through a partial reflection? Try it yourself. There's no change in colour. This must mean that whole photons are being transmitted or reflected. The splitting is purely random, like coin tossing. To understand this properly, we will need another activity that will tell us why accurate measurements need very bright lasers. The next activity is about an analogy between a beam splitter and a coin tosser, randomly selecting alternative paths. We will do activities using an online coin tosser to discover how fractional error of a random sample of photons gets smaller and smaller with increasing numbers of photons, but how the actual difference in the number of photons in each path gets bigger with more photons. Photons follow simple statistics of random samples, just like coin tossing. When you toss a coin, the probability of heads is always 50%. So why don't you always get 5 and 5 if you toss a coin 10 times? You can use an online coin toss simulator to try 10 coins and then 100. Try doing some 10 toss trials. How do the results fluctuate from trial to trial? What is the typical range of values, where the range refers to the difference in the number of heads versus the number of tails? If you do it enough, you'll find that 2/3 of the trials have a range of 2 or 4. The average range is 3.3, because this is the square root of 10. Now try some 100 toss trials. You won't get 50-50 very often, but 2/3 of your trials will be better than 45-55. The range of values will be about 10, which is the square root of 100. The accuracy will be about 1 on 10, which is 10%. Now try some 10,000 toss trials. Can you predict the range you will get? It is given by the square root rule. 100 times 100 is 10,000, so the range will be about 4,950 to 5,050, a range of 100. We were just talking about coin tosses, but all of this is the same for photons. If you could slice a beam up like salami into photon-thick circles and count the number of photons in each circle, the value would differ every time. The range of numbers of photons arriving will be just the same as for the coins. If the average was 100, then the range is 10, and so you will likely get between 95 and 105 photons in any slice. This means the brightness would be fluctuating. When a photon reaches the beam splitter, it has a 50% chance of being reflected. Therefore, the square root statistics apply to beam splitters. The number of photons that end up transmitted versus reflected will never be exactly 50-50. Gravitational wave detectors use very bright laser beams. There might be 10 to the 18 photons in every slice. The square root of 10 to the 18 is 10 to the 9. So the fractional brightness fluctuations are only 1 part per billion, which is incredibly small. Yet, even errors this size become a noisy neighbour in gravitational wave detectors. The intensity will be fluctuating by 1 part in a billion. This intensity fluctuation is called shot noise. But notice another thing. The difference in the number of photons in each beam is also 10 to the 9. That means that one mirror will be pushed by the photons more than the other. It is only 3 photons difference if there are 10 photons in each slice, and 10 photons difference for 100 photons, but for this very bright beam, it has become 1 billion photon difference. This is quite a strong effect, and it's called radiation pressure noise. Here is a very simple activity with our toy interferometer, using small objects as our photons. We like to use small lollies or sweets, but you could also use dried beans. When reflecting off the mirrors, the photons impart some momentum. In the toy interferometer, you can observe the recoil of the mirrors when one object hits compared with, say, 5 at once. You should get the idea that the randomness in the number of photons taking each path means that the photons make the mirrors move differently, just like a gravitational wave signal. This is radiation pressure noise. You could also do this activity with Nerf guns. If you have more than one Nerf gun firing at once, you'll see how more photons create more motion. Now we will look at our model interferometer and see how gravitational waves cause interference patterns. If the length of both arms is exactly the same, then light will recombine perfectly and show one bright spot on the detector. If the distances are different, then the light will simply have a different brightness. If the mirrors are not perfectly aligned, we will see this effect as a changing pattern due to interference. We can see this change in pattern if we tap the desk. Why does the pattern change? It happens because half a wavelength change in path lengths takes us from the maximum probability of a photon arriving to the minimum probability. When a gravitational wave passes through the detector, it stretches space-time, causing one arm to stretch and the other to shrink. As one arm is stretched longer and the other is shortened, it creates a path difference, and then the reverse, back and forth as the wave passes. How would the interference look if you watched the individual photons arriving? Brightest might look like this, half bright like this, dark like this. A gravitational wave changes the brightness, which means the number of photons. But as we've learnt, the photons are always random. The brightness of the fringe is always changing, following the square root rule, with the brightness changes getting less with more and more photons. But the mirrors are being buffeted by the photons, and this buffeting increases with more and more photons, again following the square root rule. So we see that the statistical nature of photons causes the detector signal to change all the time. We call this noise. You may think that you're detecting a gravitational wave, but all it is the noise. You might think that the best thing to do is to reduce the fractional error by making the laser brighter, but if the laser gets brighter, the total difference in the number of photons gets bigger. This means the unbalanced pushing of the mirrors gets worse. You can't win. More photons and the fluctuations from mirror recalls get worse, fewer photons and the brightness fluctuations get worse. This is the famous uncertainty principle in quantum mechanics. To wrap up, let's just summarize. We have seen that there are two types of noise in the detector. One, because different numbers of photons are hitting each mirror. The other is because fluctuating numbers of photons in the beam can't be distinguished from brightness changes due to gravitational waves changing the length of the arms. The tiny statistical fluctuation in the number of photons arriving at the photodetector is called shot noise. To reduce shot noise, we increase the number of photons by increasing the laser power. But increasing the power has a trade-off. If we increase the number of photons, then the number of photons hitting the mirror will have a larger range and cause more motion in the mirrors. So how do we increase the sensitivity of our detectors with all this quantum noise getting in the way? The place where these lines cross is called the quantum limit. It is the balance between these two opposing noise sources. Here is a graph showing how both noise sources are related to the laser power. Power is related to both frequency and number of photons. So, while changing the power affects the number of photons, it's no surprise that both of these noises also depend on frequency that you're trying to measure. Too much laser power and we can't measure low frequency accurately. Too little laser power and we can't measure high frequency accurately. I haven't told you the whole story. For gravitational wave detectors, we have a magic trick up our sleeves. But it's not magic, it's quantum science. With it, we can break the quantum limit. Sometimes it's called quantum squeezing, and sometimes it's called squeezing the vacuum. But this is a topic for another video. Thank you for listening, and I hope you've learned something about the quantum limit of gravitational wave detectors.